Hi, we're going to talk about the stuff from Lecture 12 today. Lecture 12 today. Right, as usual, watching these videos is not a substitute for reading the book or notes. Okay, let me start with the definition of something called a random variable. A random variable, usually denoted by capital letters, sometimes by lowercase letters, but usually capital letters. A random variable is just a plain old real variable, meaning it's a box that can hold a number. Right? And the number in the box can vary, just like it can with any variable. The thing that makes a random variable random is that the value of the variable, right, the number in the box, if you will, depends somehow on the outcome of an experiment. It may depend on it directly or indirectly, but somehow the value of the random variable changes when the outcome of the experiment is different. So here are some simple examples. We could choose an apple at random, right? Go into Kroger and choose an apple. And we could let X be the weight of that apple. Right? And then if I chose a different apple, then the value of X would be different. Whatever the outcome of the experiment is, that's the value of the random variable gets set accordingly. Okay, here's a slightly different one. We could go into Kroger and choose a box of blueberries. I can write that at random, right? And let X be the number of whole blueberries in the box. The reason I bothered with these two examples, even though they seem very similar to one another, there's actually an important difference, and that is the difference between continuous and discrete. Just as with data sets, random variables can be continuous or discrete. And you know how you decide for a data set whether it's continuous or discrete by thinking what values. The data set has to be given by a description for this to make any difference. And you think, well, what values could fit that description? What are the possible values that could be in the data set given that description? Well, here you just think the same thing. What are the possible values of the random variable? Right? If the possible values of the random variable can be any number in some whole interval. Let's put 0 here. Let's suppose this is the minimum possible weight for an apple. And maybe over here is the maximum possible weight for an apple. Then any number in between, any real number in between, can be the weight of an apple. So if you graph that on a number line in the usual way, it would just be a solid line covering the whole interval. If you thought instead about the number of blueberries, right, well, you could have 0 or 1 or 2 or 3 or 4, right, and so on. You could have, I don't know any idea what the maximum is, but certainly you could have no whole unbroken blueberries in the box, or 1 or 2 or 3, but you can't have 2.5, right, or 3.14159. You can only have these certain discrete values of this random variable that counts the number of blueberries in a box. Right? If you graph them on a number line, you see individual dots separated by spaces, and that's a discrete random variable. One more little example, just to point out one little thing. So suppose I choose 10 apples at random, and I let X be the average weight of the apples. The reason to include it is that in these cases, the value of the random variable was immediate from the outcome of the experiment, right? You weigh an apple, that weight becomes the value of x. You choose a box of blueberries, the number of blueberries, whole blueberries, becomes the value of x. Here, you'd have to choose the 10 apples and then weigh them and make a calculation to get the value of x. So the value of x can depend upon the outcome of an experiment in a sort of indirect way. It doesn't have to be exactly the same as the data you would write down. It could be something calculated from that data. Okay. Let's talk a little about probability distributions. We're still doing discrete stuff here. And the definition of a probability distribution sounds different for discrete and continuous random variables. And we're going to, for a little while here, we're going to be working only with discrete, but I'm going to mention the definition of the probability distribution of a continuous random variable, and then we will come back to it later. Right? For a discrete random variable x, I'm just going to abbreviate RV. For a discrete random variable x, the probability distribution is just a table that lists each possible value of x and the probability that x has that value. For a continuous random variable x, for a continuous one, the probability distribution, it's really a probability density function. It's where it's going to be a function that can be used to find the probability that the value of x is in any given interval. That's not going to sound like the same thing at all. It's not going to look like the same thing at all. But if you know enough about this stuff, it's really not that much different. Anyway, as I said, we'll come back to those. Let me do a couple of examples here. So, the first one. 2 fair six-sided dice are rolled, and the value of x is the sum of the dice. Construct a probability distribution for x. Okay, so what are the possible values of x? Well, the possible values of x are the possible sums that 2 dice can have. So that would be 2, 3, 4, and so on. So I'm going to call that little x, the values of x. And so the possible values are 2, 3, 4, 5, 6. Well, I might not have the patience to fill all this out, but maybe. So the probability distribution table has to show each possible value of the random variable and the probability that the random variable actually has that value. So it can be written as the probability that x is actually equal to x. The random variable x actually is x. Sometimes you just write probability of x for that. All right, so what's the probability that this random variable x has the value 2? Well, x has the value 2 if the sum of the dice is 2. Okay? And so the event, get a 2 is the event containing only the single outcome 1, 1, right? You have to have a 1 on each of the dice. You remember the table that showed all of the outcomes in the whole sample space for 2 dice. There are 36 of them. They're all equally likely because these are fair dice. And so the probability of getting a 2 is 1 out of 36. Well, the probability that x is equal to 3, that is the probability that the sum of the dice is 3, right? You would look at the event get a 3. It would contain the two outcomes 1, 2, and 2, 1. Those are the only ones that lead to a 3. So the probability that this random variable is equal to a 3, again, that's the probability the sum of the dice is 3, and that's the probability that this event occurs. So you get one of these two outcomes. So the probability is 2 out of 36. And if you did the rest of these, you'd see that this is 3, 4, 5, and 6 out of 36 is the probability of getting a 7. That's why 7 is so important in Game of Craps. And then it starts to go back down. Okay. And there's the probability distribution. Again, it shows each possible value of the random variable, and it shows the probability that the random variable actually has that value. Okay. Here's another one. A psychological test was administered to 150 people. Possible final scores on that test were 1, 2, 3, 4, and 5. Here were the results. So here is, this really should have been a lowercase x for the value of the random variable. Right? X, the random variable x is the score. Okay. So what does this mean? Frequency 24. This means 24 people got a 1, 33 people got a 2, and so on. And obviously we're going to, unlike the example before where we figured out probabilities from a theoretical probability sort of thing, here we're going to have to do empirical probabilities. Empirical probabilities are really just relative frequencies. So that's really what we're going to be doing. We're going to be making a relative frequency table. Okay, so the random variable is the score. Right? And so the possible values of the random variable are 1, 2, 3, 4, and 5. And then we have to figure out the probability of each of these. The probability that the random variable has the value 1. Well, there are 150 people altogether. 24 of them had the score 1. So the probability, the empirical probability here, of 1 is 24 out of 50. This one's 33, 24 out of 150. 33 out of 150, 42 out of 150, and so on. Okay, not much to that. Let's do the next part. What is the probability that a randomly chosen participant's score was a 3? Well, that one I can read right off the table. Okay? It's just 42 out of 150. What's the probability that a randomly chosen participant's score was greater than 3? Well, the event greater than 3, that's the event that you get a score of 4 or 5. And you know how to find the probability of an event with two outcomes in it. You add the probabilities of the two outcomes. This is going to be the probability you get a 4 plus the probability you get a 5. So this is 30 out of 150 plus 21 out of 150, or 51 out of 150. Okay. One more here. Assuming that the sample space for an experiment is these 5 possible outcomes, A, B, C, D, E, what value for the probability of D makes this table here into a probability distribution? Well, what are the rules that probabilities have to follow? Right? One of them is that the probability of the whole sample space is 1. So you need all these numbers to add up to 1. So all you have to do to find a probability here is to add up the probabilities you have and subtract from 1. Whatever you get, that's what has to go right here. So the probability of D, in other words, is just going to be 1 minus the probability of A plus the probability of B plus the probability of C plus the probability of E. And let's see, this is 0.35, 0.65, 0.9. So 1 minus 0.9 is 0.1. That's what would have to go in there. Let me just say that sometimes you are given a whole table like this and asked if it is a probability distribution. The things you need to check then are whether the probabilities add to 1, and also you have to remember that each of the probabilities needs to be between 0 and 1. Right? All right. Excuse me. A couple of other little things here. First, we want to talk about the expected value, right? Sometimes called the mean of a random variable. If you have a random variable, so x is a random variable, possible values of x are, let's say, x1, x2, x3, and we don't care how many there are. And also, we know the probability. The probability that x has the value x1 is little p1. The probability that x has the value x2 is p2, and so on. Then the expected value or mean of x is, and it's given by this formula here. I use square brackets for expected value usually. Some people use parentheses. Both are very common. Okay. What you do is you take each of the possible values and multiply it by its probability. So x1 times p1, x2 times p2, and so on. And then you add all those little products together, however many you have. And that's the expected value or mean of the random variable x. There's a great deal that can be done with this, and we won't do very much of it at all. It's something you should know about. You should know it exists. And as I said, a huge amount can be done with it, and you may see that done in further courses. So let's do a little example here. Find the expected value of the probability distribution shown here. So we have the values. I'm going to call that x. The probabilities, right? This is the probability of each of the x's. The values are 1, 2, 3, 4, and the probabilities of each one of those values is given. What do we have to do? We have to multiply, remember the formula for e of x. It's going to be the first value times the probability of that value plus the second value times the probability of that value, and so on. So what we have to do is we have to take each value and multiply it by its probability and then add all of those together. So what I'm going to do here, I'm just going to extend this table. Right? I'm going to put in value times probability. So 1 times this, obviously, oh, for goodness sake, 12/36. 2 times 10/36, so 20/36, 24/36, another 24/36 for 4 times 6/36. And then once I have value times probability, what do? I just add these up, right? So the sum of this column here is, let's see, 32, 56, 80. 80 over 36. Right? So the expected value of this random variable x is 80/36. Okay, that's as much as you will need to do for expected value of a discrete random variable. It could also be called the mean. You might be asked for the mean of the random variable x, and you would make the same calculation. Those mean the same thing. No pun intended. Okay. Just a few words about variance and the standard deviation of random variables. They can have variance and standard deviation. You could think of the set of all values of a random variable as being a data set, right? And then compute the variance and standard deviation of that data set. And that would be the variance and standard deviation of the random variable. It's the idea is simple. We won't learn anything really more about calculating these from certain random variables, except in a couple of special cases, which you'll see later. I do want to say right now that either one of these, I'll just talk about the standard deviation, but either one of these can be used as a measure of risk. The standard example is stock market risk. If you think of buying a stock, you buy it for a certain price. Let's say you buy it for $100. And at some point you want to sell it, and you want to wait until it gets more valuable, until the price goes higher before you sell it. But there may come a point at which you have to sell it. Right? You have to sell it because you need the cash. Maybe you borrowed money and you have to pay it back, or whatever. There are many reasons to need cash. Right? And so it's going to be important to you that if you are forced to sell the stock, that you can rely on not losing too much. Right? So consider these two stocks right here. This is also 100. Here's a stock. It starts out at 100, and the price varies like this. Right? You've all seen stock market prices. This is the date, of course. Let's say it's in days. Right? Sometimes it goes down, sometimes it goes up, but for the most part, it doesn't vary very much from $100. Here's another stock. This one, the price varies much more. Now, if you're worried that you might have to sell the stock one day, which one of these would you pick? You would, of course, pick this one because the price is never, in the past at least, it hasn't been very far from $100. And so if you're forced to sell, at least you won't be selling at a very low point. Whereas in this case, you could, if you were forced to sell and you don't know when that might happen, right, the stock could be down here. Right? You could lose most of your money if you were forced to sell. Whereas here, that would be very, very unlikely. Well, if you think of, right, what we have here is days, and what we have on this axis is the price. If you think of these values, of the daily values of the stock, you could think of plotting those on a number line, right? There's 100, and these, on this pick, from this stock right here, you would expect the values kind of to cluster right around 100, with very few farther away. Here, on the other hand, you would expect values much more spread out. Right? If you think of these as data sets, this one's going to have a much smaller standard deviation than this one. And so the standard deviation is used to measure the risk involved in buying a stock that you might have to sell. Right? That's called volatility, by the way. The volatility of a stock is how much it varies. And if you want to look up something about it, the famous index of that is the VIX, which all traders follow. All right, that's about it for this section.